Okay, so let's start. So hi everyone, good evening. I am Prakash Joshi. I welcome you all here on the behalf of Grothendieck School of Thoughts in this fifth lecture of the talk series Modern Homotopy Theory. So as you know, initially this talk series was running in offline mode here at ISER Mohali, but based on your responses, we decided to shift this in an online mode. So people who could not join first 4 lectures can see the lectures note on our website, and the recorded video lectures will be uploaded there soon. By the way, further information is that we are soon going to release registration form for the next talk series K theory. So if you are interested, you can fill that form also. A further information is also that there is a studentship form available on our official website. So by filling up that form, you can get all the information about all courses. So if you are interested in learning these stuffs or modern stuffs in mathematics, so you can take a studentship form. You can fill a studentship form also. And the another information is that as you may be aware of, because we write these things in last mail as well. So we are going to extend our organizing team. I hope that you are aware of this, that we are launching our faraway team. Means this team will work as a bridge between us and your institute, the institute in which you are learning. So basically a member of this team is going to act like a bridge between us and his institute just by forwarding our invitation and some other things, means usual things what the organizer should do. So if you are interested, then you can look up on our website and fill this form for registration form for our faraway team. Till now we have 5 members for our faraway team. That is ISER Mohali, ISER Kolkata, ISER Pune, ISER Tirupati, and IIT Delhi. We are expecting that you all will join and make these things more good. Okay, so now coming to point. So as you may be aware that the speaker for this talk series is my colleague Dipankar Methi. His area of interest is homotopy type theory and higher category theory. In this talk, he will talk about cylinder objects in abstract categories. So let's over to you, Dipankar. Take your charge.
Hi. So I don't know why the number of participants is this much, because we had almost around 50 responses. But anyway, whatever this is, let us start today's session. So can you see my screen now?
Yes.
Okay. All right. Okay, so in the last few lectures, what we have discussed till now is a particular viewpoint of what homotopy theory for topological spaces offers us. So what we have done is we looked at the category of topological spaces, and we extracted the information that the first observation that one can make from homotopy theory is that more than isomorphisms in a given category, which is in this case top, we have a further class of morphism which does not really affect the theory, namely the class of homotopies. Okay, so homotopy equivalences, rather. Homotopy equivalences. So these are the class of continuous maps. So more than isomorphism, which are homeomorphisms, we have a larger class of morphism than them, namely homotopy equivalences, which does not really bother us when we try to study the when can you treat them as a natural analog of homotopy equivalences? Well, this notion was given by the idea of localization at the class of morphism sigma, So what this functor basically does is that it inverts all morphism in sigma and tries to identify objects in C which are isomorphic in the category C sigma inverse. What is this happening? Can you hear me? Okay, there is a problem, I guess. Can you share? Can you see my screen?
No, your screen is not shared.
Okay, I'll stop sharing. Can you see now?
Yes.
Okay. So, yeah, so coming back to what I was saying is sometimes while starting a particular category or a theory, we are interested in a sub-theory where we try to force a class of morphism to be interpreted as something similar to homotopies, which does not really bother the study of the problem that we are going to consider in the category C. So this was given by the idea of localization, and the model we had in our mind is C for top and the homotopy category of top of topological spaces, and this functor was basically given by identifying topological spaces up to homotopy, and the class of morphism that we are modeling was the class of homotopy equivalences in top. And this category is actually the category of homotopy types. Okay, so this was the first idea that we tried to extend from top to a particular category C. Now, in this session, what I am trying to convey to you is that instead of forcing a class of morphism to be treated as homotopy equivalences, why don't we try to generate homotopy equivalence? So suppose C is a category. How do you think of a morphism to be some sort of a homotopy? So to talk about that, one should first of all say when two morphism in the category are homotopic, right? So that is the first thing. So if F and G are two map, when do you say that they are homotopic? So this term homotopic does not have a meaning yet inside C. We're trying to give it a meaning. And once we have that, what we are going to do is that we're going to define a map from, let's say, A to B to be a homotopy equivalence if there is a map G such that G compose F is homotopy equivalent to identity and F compose G is homotopy equivalent to identity. Okay? So we can do that, but before that, we should describe what it means to have a homotopy between two maps. But even before that, we should talk about intervals, right? So the first thing that you have in the category of topological spaces to study homotopy theory is the notion of an interval, right? But you see, if you take two topological spaces X and Y and two continuous map F and G, to define the notion of homotopy from F to G, we don't really need the interval. What we rather need is the product X cross I. So a homotopy is given by this data, right? It's a continuous map from X cross I to Y, such that H restricted to the left hand point 0 is given by F, whereas H restricted to the right hand point is G, right? By the way, if at any point you have any question, you can stop me and ask, okay? Or you can also put that in the chat box. So this is the idea of a homotopy, but you can also write it in a similar fashion by saying that, you see, this left-hand point 0 is not really essential. What is rather essential is the inclusion of X inside X cross I, right? which is sending x to x comma 0, the left hand inclusion. And this condition is just given by H compose with this map. Let's say this is called E0. So this particular composition is given by F. And there is this right hand inclusion, which is E1, I'm going to denote, which sends x to x comma 1. Okay, no space to write, but anyway. And this condition translates to saying that H compose E1 is equal to G. So the idea of this interval, it's not really necessary. What is rather necessary is this object x cross I as a topological space, and this two particular map, namely E0 and E1. Okay. So that is what you need to define homotopy for topological spaces. Moreover, to make sure that this behaves like an interval, what we need is the projection map from x cross I to x, which is not only a projection, but also the contraction of this object to x. Okay? There's this projection on x, which is actually a contraction on. So what this guy is doing is basically this particular object x cross I, it is basically factorizing the diagonal, the co-diagonal map x disjoint union x to x, right? So the picture is, so if you think of the interval, and let's say x is this guy, then the product x cross I is actually a cylinder, topological cylinder, and this end E0 is actually excluding, it is actually putting x as the left hand side of the cylinder x cross I, whereas E1 is putting x as the right hand side of the cylinder x cross I. So this is basically a cylinder on x, at least pictorially. And then there is this projection map, which is squeezing this whole cylinder to x, okay? And such that this projection, when composed with E0 and U1, gives you identity, right? Because this is projection and this is just including x inside this left hand side. So if you look at PRX compose E0, this is identity on x, and also PRX composed with E1 is also identity on x, right? So to define the relation, what we call homotopy in topological space, what we need rather is the idea of a cylinder, which is a topological space, such that it has two copies of x and can be squeezed to x. So this is what we are going to abstract out for arbitrary categories. Therefore, there comes the definition of a cylinder object. Let C be an arbitrary category. And x be an object in C. A cylinder object or I should rather write a cylinder structure on X. A cylinder structure on X is an object which I am going to denote as Cyl of X with two map E0 and E1 from X to Cyl X, and another map P from cylinder of X to X, such that P compose E1 is equal to 1x, which is equal to P compose E0. An equivalent way of saying the same thing is that a cylinder object equivalently, so a cylinder object or a cylinder structure on X is a factorization of the codiagonal map. Because of this condition. Right, so that is a cylinder structure, and immediately you can conclude that in top, okay, in top, X cross I is a cylinder structure, has a cylinder structure, has a cylinder structure. Okay. Because of this two inclusion map, left hand inclusion and right hand inclusion. Exactly the same E0 and E1 and P as PRX. Okay, now once we have defined what a cylinder object could be in an arbitrary category, we can right away say when two morphisms are going to be homotopic, in the following notion. So in the same line of argument, if X and Y are two objects in the given category C, and F and G are two arbitrary map in C, then we say that F is homotopic to G if there exists a map H from cylinder on X to Y such that H composed with E0 is equal to F and H composed with E1 is equal to G. Is that clear? Is it clear till now? Okay, thank you, Rajat. Okay, you might ask me now, why am I doing this? Let me give you some other example and let me show you that what we do in other areas of mathematics are actually something similar to what we study in topological spaces. Namely, many areas are actually homotopy theories. Okay, let's take this particular category. But before that, what is another area where you have heard this term homotopy other than the category of topological spaces? Any other space, any other area in mathematics where you have heard this term homotopy? Well, it's the category of chain complexes, right? And chain maps. There is this. Oh, I see. Prakash is there is a comment by Vishwanath that.
Yeah, I will do that.
Yeah. Now you can speak, maybe. Vishwanath, you can speak now.
Yeah, I will.
Yeah. All right. So think of the category of chain complexes of R modules, double-sided R modules. There you have heard this term called chain homotopies, right? And then chain homotopy between chain maps. But have you ever wondered why they are called homotopic? Of course, there is a historical reason that while studying homotopy theory for topological spaces, in particular for CW complexes, you could actually create chain complexes and take homologies. But apart from that, have you ever heard of or have you ever questioned yourself why this particular area has this term homotopy? Let me give you the idea. So what I'm going to prove is the following message, that chain homotopies are homotopic in the sense that I have defined. Okay, so a Cyl-homotopic. So from now onwards, whenever I say cylinder homotopic or Cyl-homotopic, I mean categorically homotopic as defined in this way. Okay. So there is a cylinder structure in the abstract category, And according to that, there is this given notion of homotopy in that category with respect to that cylinder object. So this is the term Cyl-homotopic, or sometimes I may equivalently write capital homotopic. Anyway, so the message is that chain homotopies between chain maps of chain complexes are actually cylinder homotopic. That is, there is a cylinder structure in the category of chain complexes of R modules, such that the corresponding cylinder homotopy is actually chain homotopy. Let me show you how. Okay, so suppose X is a chain complex. Then I want to define Cyl of X dot. Let me give you what this looks like in particular. So in degree n, this guy is given by 2 copies of xn and then another copy of xn minus 1. I'll come to that why this is the description of the cylinder object. But before that, let me show you that this actually does work. And what are the maps, the differentials? Well, xn minus 1. Yeah, this is decreasing, right? Yeah, xn minus 2. And the differential is given by sending x comma y comma z to, what do you do? So you send this to dx minus z, comma dy plus z, and comma minus dz. So this is the description of the cylinder object on X. Now, when you say that two chain map a cylinder homotopy, what does it mean now? I have given you a cylinder structure. Okay, to specify what the other maps is, the other maps are, I should mention this particular components, right? X dot to cylinder X dot, E0 and E1, right? Let me specify them. So what E0 does, E0 on n, on degree n, it takes x to x comma 0 0. So it sends it includes the x on the first copy, so this particular copy. What E1 does, it takes it to the second copy, so 0 y and 0. So what is happening inside is so one component is E0, another component is E1. You can think of it as a triangulated cylinder. And then the other map, the projection map, okay, where I write this? Yeah. So the projection map on X is given by sending x comma y comma z. What do I write this? Okay. So Pn of x comma y comma z is given by x plus y. Okay. All right. Now the description of the cylinder object is complete. So now the question is, if f and g are two chain maps from x dot to y dot, when are they cylindrically homotopic? Okay. So according to the definition I have given here, this says that f and g are going to be cylindrically homotopic if there is a map H from the cylinder on x dot to y dot, such that H compose with E0 is equal to F and H compose with E1 is equal to G. Right? Now, what does this mean component wise? So component wise, this means that Hn of E0 n of x is equal to fx, right? But this guy is then given by x comma 0 comma 0, which is fx. So on the first component, so component wise, this looks like this, right? Xn plus xn plus xn minus 1 to yn. So on the first component, this is given by f. Whereas on the second component, this is given by g. But there is also a third component, right? Which is Hn of 0 comma 0 comma z. So this guy is from, okay, so if I put blank on z, then this guy is actually a map from xn minus 1 to yn, right? Moreover, H has to be a chain homotopy. Sorry, it has to be a chain map. Because it's a map in the given category, it has to be a chain map. Right? My claim is now that this precisely, this data, which you can write as Hn, is actually a chain homotopy from F to G. So Hn from xn minus 1, sorry for that. Xn minus 1 to yn is a chain homotopy. From F to G. Okay, so shall I prove that, or shall I leave that as an exercise? Would you like to check this, that this does work? Well, basically a chain homotopy is given by this data, right? So a chain homotopy, so this is the picture, xn plus 1, xn, then xn minus 1 over here, and then you have f minus g, or g minus f rather, g minus f, yn plus 1, then yn minus 1, and at each component you have gn minus f. So a chain homotopy is given by this status, right? This is Hn and this is Hn. Such that this composition, so if this is T, so such that dH plus HT is equal to G minus F. Right? Now, write down explicitly what it means for Hn to be a chain map. Then you can actually prove that two map G and F, sorry, F and G are homotopic, chain homotopic, if and only if they're cylindrically homotopic. So this is an exercise. This is a nice exercise. You can try this out. But now you have this view that in the category of chain complexes, you actually have a homotopy theory. Okay, you might wonder, where is this interval? Where is the interval in this particular case? The interval is the following, but it is not exactly the interval that you think of. Okay, so this particular case is really the point of studying homotopy theory without an interval. Okay, so think of this particular chain complex, which is 0 at every degree. At the 0th entry, it is R. So this is the 0th entry. And at the, okay, so this is not the 0th entry. So this is decreasing. So yeah, so this is the first entry. And then at the second entry, you have 2 copies of R and the others are 0. And what is the differential? This is precisely 1 comma minus 1. X is sent to x comma minus x. All right. And then what you have defined as cylinder on a chain complex x dot is actually given by the tensor product of x dot with with I, tensor product. So elementarily, this means that this is the sum over x and x. So component wise rather. So component wise, if you have C dot and D dot, then component wise, their nth component is given by Cj, okay, sum, but tensor product, tensor over R with Di such that I plus J is equal to that. Now write it down for this particular I, and then you can check that the cylinder I have defined is actually the tensor product. So there is an interval object for the category of chain complexes, but it is not really the case that that the cylinder is given by product on I. So in the category of topological spaces, what we have in top, whereas we have so in the category of topological spaces, we have the cylinder X is actually given by product with I, whereas in the category of chain complexes, this is given by product, but not necessarily the categorical product. It's actually the categorical dual product, namely the tensor product. Right? So the cylinder is not really given by the product structure, though you have an interval. Okay. So the first message was this one, that in the category of topological spaces, homotopics between continuous maps are cylindrical homotopics in the abstract sense. And so is the case for chain complexes. Okay. There is another message for category theorists. Okay. Whoever is interested in category theory, maybe. Sorry. The following message is that natural transformations are also homotopics, cylindrical homotopics. Natural transformations are Cyl-homotopics. That is in the category of in the category of small categories. Okay, you can forget about size issues and can take all categories actually, but let me stick to this. So in the category of categories, there is a cylinder structure. There is a cylinder structure. And by that, what I mean is that if C is a category, well, not object-wise, I can actually give you an interval which is standard. So the interval in the category of categories is given by two objects. Okay, I'll write 0 here and 1 here and 1 arrow. So this is the only arrow which I'm going to denote as I. There is a single arrow from 0 to 1. There are two objects only, 0 and 1. And of course, there are this identity maps, 1, 0 and 1, 1. Apart from that, there is a single morphism I. Okay. So this is the interval. And then cylinder, in this case, actually, I'll not write X. Cylinder on a category X is X cross I, the categorical product. So, okay, X is the category. Now, why I'm doing this is the following. If I define, okay, is this clear that this is categorical product? So objects are pairwise product. So objects are pairs from X and I, and morphisms are also pairs from X and I. Is that clear? Anyway, so now along this line of definition, what is a homotopy between two functors? Let's say X and Y are two categories, and now F and G are two functors. So along this line of definition, these two are homotopic. That is, there is a homotopy from F to G. I'll not write an arrow. There is a homotopy from F to G. If there is a functor from the cylinder on X, which is actually X cross I, to Y, such that H, okay, I didn't define what the components are, what the endpoints are. Okay, so let me do that. E0 for this particular case, E0 is given by sending this to the zeroth component. Okay, how do I do that? X to X cross I. So what it does is it takes an object X and sends it to X comma 0 and takes a morphism X to Y, X to X prime to the corresponding map. F, an identity on 0. And similarly, E1 takes this to 1. Okay, instead of sending X to X comma 0, it sends X to X comma 1. So the right endpoint, E1. So to say that two functor are homotopic along this particular cylinder. Oh my God. Yeah. So along this particular cylinder, if H compose E0 is equal to F and H compose E1 is equal to G. What this means in particular is the following. So you have X to Cyl. Okay, I'll not write Cyl again. I'll write X cross I, then to Y. So this is H. And then there is this E0 and E1. And composing this yielding F says that H, so if you think of H as a functor now, which is the case actually, then object wise, sorry, anyone speaking? Who is it speaking? Is there a doubt or something? Okay. Yeah, so what I was saying is giving a functor like this means that for every object X and 0, I'll have to give you an object H of X. Right? And since this guy is actually E0 of X, so this is E0 of X, this guy should be F of X. Right? Similarly, if you look at X comma 1, this guy is E1 of X. And this guy by H would be sent to H of X comma 0. Should be H of X comma 0. And H of X comma 1 should be given by G of X. But note that there is a map, right, from iPad is not very competent. This is my E0 of X. And there is an obvious map, right? Identity on X and the corresponding single map I in the category I. Right? So H being a functor, this has to send this particular morphism somewhere, right? Let's denote this. Let us denote this by, let's say, what, HX. Let's say. I'll write eta maybe to make sure that you understand it. So let's denote this by eta x. So eta x is actually the functor H being evaluated at 1x comma I. This is precisely the data that you need for defining a natural transformation from F to G. But of course, there is this condition of some diagrams being commutative that you can actually write down. but it will follow from H being a functor. Okay, so there is this commutative diagram. So this particular commutative diagram, fx to gx, this is eta x, and fy to gy, this is eta y. This guy is given by ff, let's say, and this guy is gf for a map from x to y, f. And if you compose this two, so gf compose eta x, what is this guy? G of f is actually h of f comma identity on 1, whereas this guy is h of 1x comma I. So this side is h of f comma I. Similarly, if you compute the other side, which is eta y compose ff, this is also h of f comma I. And these two are equal, therefore this and this are equal. Sorry for this mess, but anyway, the point is h being a functor from this category to y. Okay, maybe. Yeah, so h being a functor from x cross I to y, make sure that the same data gives you a natural transformation from x to g. So the message is that natural transformations are actually homotopy. There are other areas as well which we could touch. Am I running out of time? No, right? So let me give you another example. By now you might be thinking that, okay, in every place you actually have an interval object. In the category of topological spaces, you have the standard interval. In the category of chain complexes, you at least have something like an interval object. Also in the category of categories, you still have an interval. Then why did you say that intervals are not really accessible everywhere? Let me give you another example where the interval is actually not accessible. So
how you are getting idea that in some category interval exist or not, means
it may not exist. That's the point.
So how means how to think in a category, means like if this interval exist or not?
No,
how you will find?
See, there is, first of all, there is not a unique interval if at all it is there.
Okay.
And secondly, it might not exist. Okay.
Okay.
What is rather important is the cylinder structure. In most of the cases, it turns out that there is an interval such that the cylinder is actually given by the product with this or some other categorical structure with I. But it is not necessary. See, for example, if you take any category, there is this trivial cylinder, right, which is identity. So what you do is, if C is a category and X is an object, then this diagonal, see, to define a cylinder on X, you actually have to factorize this co-diagonal map, right? But you can take this factorization itself, take identity on X disjoint union X, and take the co-diagonal. This still factorizes the same diagram. So there is this trivial cylinder structure on every category. So this might be the 0th example. But this does not really give you any interesting homotopy theory.
Okay.
Because the homotopy equivalences that you generate are nothing more than isomorphisms. So you are not really studying a new theory.
Okay.
Maybe at this point I should touch upon what homotopy equivalences are. Okay. So along the same line of definition, I can say that when two maps are homotopy equivalent, I'll write that here maybe. What should I write that? Yeah, maybe I'll write that somewhere here. I'll edit that in the note, but for now, let me write that here. So F from X to Y is an homotopy equivalence if there is G from Y to X such that F compose G is homotopy equivalent to 1, whereas G compose F is homotopy equivalent to 1 on, so this should be on X, this should be on Y. Or I should actually write.
Cyl-homotopic, na?
Yeah, Cyl actually you should write, but I'm dropping it now.
Okay.
I mean this. Why I'm writing this will be clear in a minute. But you can define something to be a homotopy equivalence along this given cylinder. Then in the category of topological spaces, two topological spaces are homotopy equivalent if and only if they are cylindrically homotopy equivalent. Similarly, in the category of chain complexes. Now, what about the category of categories? Well, that does not really give you anything interesting. All it says is that a functor f from C to D is Cyl-homotopic, Cyl-homotopy equivalent, is a Cyl-homotopy equivalence if there is a functor G from D to C such that there is a natural transformation eta from G compose F, or whatever you write, G compose F or F compose G, to identity on C, and a natural transformation from 1D to F compose G. This is close to being an adjunction, but this is still not. One suitable thing that we can do to modify this is by improving our category I. So you see, in the category of topological spaces, one nice thing about the interval is that you can really reverse the role of 1 and 0, the two endpoints, right? So once you look at it closely, you have the idea of reparameterization for topological spaces. So if you have X cross I to Y a homotopy H, then you can actually so if H is from F to G, then in the category of topological spaces, you can reparameterize this by you can reparameterize this by defining H of X comma T to be H of X comma 1 minus T, right? You can do this. So the left end point and the right end point are really interchangeable. So what you can do in the case of categories is we can improve our interval by adding an arrow in the reverse direction, which is an isomorphism. Okay, so I can add J such that I compose J is equal to 1 and J compose I is also equal to 1. Then this cylinder, this interval is actually somewhat like a contractible object. Now, if you do that, then what you find is that for this particular interval, what I am going to denote now as J, so J is this particular category. It has two objects, 0 and 1, but those are isomorphic. So there is this I and J, because that I compose J is identity and J compose I is identity. If you take that and you define a new cylinder object in the category of categories on a category X, it should be given by X cross J once again, X cross J. Then you can check that two functor F and G from X to Y are homotopic, or J homotopic, I should write, or Cyl-homotopic. If there is a natural isomorphism, if and only if there is a natural isomorphism from F to G, a natural isomorphism. Now, so the other so the inverse of the natural isomorphism would be given by the images of J. Now, if you look at what happens in this case to homotopy equivalences, then you will find the following. So this I am leaving as an exercise, but this is trivial. So a functor from X to Y is a J homotopy equivalence, okay, along this J, or Cyl-homotopic equivalence. If and only if F is a categorical equivalence. So two categories are equivalent if and only if they are cylindrically equivalent along this. All right, so we have captured a lot of areas in terms of cylinder objects and homotopies. But you see, at every point, you are actually having something like an interval object. This is my point. This need not be necessary. Let me give you one example where there is no interval object at all. Okay.
Why in our example this is not adjunction, means why they are not working as unit or co-unit, this eta and epsilon?
There is a problem, right? There has to be the compatibility between eta and this is not really a problem. This is a missing data, right? You need to make sure that eta and epsilon are compatible.
Yeah. And
that, see, adjunction is an existing idea. I'm trying to convey to you that this this method gives you some information, some homotopical information. And adjunction is not really a homotopical information, to be precise. But you can make it.
You just point out that this is not adjunction, so that's why I'm saying that it is.
No. So see, for this to be an adjunction, eta and epsilon should be compatible, right? This diagram should commute.
Yes.
FGF to F to FGF to F. So this is given by F eta and then epsilon F. This
F
should be identity, right?
The map should be, first one should be F epsilon and then sorry.
Yeah. Anyway, this is epsilon and this is eta. So this should be identity on F, right? But this I didn't. This does not really. It cannot be captured in the idea of cylinder. There is a problem in it. I'll come to that. But this is basically a higher homotopical information. So whatever I have been discussing till now is actually one-dimensional homotopy theory, meaning you cannot really talk about higher homotopies. So the problem is that in all of the examples, the cylinder object is not really so nice. So what we need to define or to deal with higher homotopies is that cylinder objects commute, right? So basically what I'm trying to say is that X cross I, it should be X cross I cross I, right? And there should be a notion of I cross I in the category. But just giving a cylinder object does not really give you an I cross I. In the case of topological spaces, you were lucky that you had I cross I. Is that clear? Yeah. In this particular case, categories, you have to define something called I cross I.
Yeah.
So this is a higher dimensional cylinder. You can think of it not as a cylinder, but as a box on X. A cylindrical box on X. So you have to define this for categories. Then you will see that adjunctions are actually like homotopy equivalences, such that the homotopy components, this particular components, this eta and epsilon, are box equivalent. Okay. Does that make sense to you?
Yeah.
All right. So nonetheless, if you modify this interval I,
there is a question on chat box.
Can we define this box in abelian categories? Yes, but one has to be precise by what particular cylinder that you are talking about. So this box, see, this box has something to do with the cylinder that you have already given us. It has to be compatible with the cylinder that you have already given us. So you have to specify which particular cylinder that you are talking about in abelian category. Okay. I can give you one example, then you can think of. I'll leave it as an exercise to you of what the box object should be in this particular example for abelian categories. I mean, one can specify several examples, but since you specified abelian categories, let me give you an example. Okay. what property are you looking for in this box? Why not just take it as cylinder X? I understand. So that's what I was writing, cylinder of X. But there is a problem associated to this. Okay, where is the example? See, the problem is over here. So in the category of topological spaces, so this side, this is Cyl of X of Cyl, sorry, Cyl of X, right? On the other hand, this guy is what? This guy is X cross Cyl of I, right? And these two are isomorphic. What I'm trying to talk about is that to define a higher homotopy, see, when you study higher homotopy groups, let's say, you do not really look at this object, X cross I. You do not look at this component. You rather look at this component, X cross I square, right? This is essential. But these two are not equal in other categories. So we'll come to that, why cylinder objects are not really compatible with the cylinder, an arbitrary cylinder itself. So anyway, before we discuss that, let me say something about the abelian category that I was saying. Is that clear? Whoever said this? Yeah. So let us take an abelian category. In fact, for this part of the discussion, you can think of an additive category. Abelianness is not needed. So A is an additive category. Or an abelian category. This might be a bit more heavy for others. So to define a new type of homotopy theory for abelian categories, you have to give me a shifting map or any functor from A to A. Suppose you are given a functor from A to A, T. One should rather write sigma, but let me write T only. And a map epsilon from identity on A to T, a natural transformation. Suppose you are given a data like this. So for example, in the category of chain complexes, you can take this T to be the shifting map. Or maybe in the category of abelian groups, you can take the free abelian group generated by the group itself. Any monad would work actually. So anyway, suppose you are given an additive category with a functor, an endofunctor, and a natural transformation like this. Then you can define a cylinder object. So if A is an object in A, then you can define cylinder on A to be given by A direct sum JA, TA. And the components E0 and E1, this is A. E0 is given by 1, 0, whereas E1 is given by 1, epsilon A. Okay. This is E1, and the projection map is given by just the projection on the first component. Okay, so this is P array. Indeed, P array compose E0 is equal to identity, and so is for E1. Now check that this does serve the purpose. Oh, I just specified it. Cylinder is actually a cylinder structure. There is not much to do now. So I have given you a cylinder structure for an additive category, given an endofunctor and a natural transformation to that functor from identity. Now, the question is, when are to map homotopic? So this is the question. When are to map in the category F and G, X to Y are homotopic. Then when are two maps homotopy equivalent? is a homotopy equivalence. Okay. And is this cylinder object compatible? Is this cylinder compatible? And by this, what I mean is, if you look at the cylinder on A, this is going to be what? This is going to be this is going to be cylinder of A, direct sum T of cylinder of A, right? And this guy is A plus TA, and this guy is, if you assume T is an additive functor, then this guy is going to be TA plus TTA, right? On the other hand, if you have cylinder of the cylinder on the terminal object, which is 0. So this is, so you can think of I being I to look like the cylinder on 0, and then you take the product with A. This is not really the case, right? So cylinder on cylinder 0 is basically everything being 0. This is A, and these two are not really equivalent. Okay. So the point is that cylinder of cylinder does not work for higher homotopies. You have to give me a compatible notion. So anyway, maybe this part will come back to when you study additive homotopies, but this exercises you can check when maps become homotopy equivalence for this particular example. Okay, so we have given you several examples, but one important aspect of doing this is that we are trying to mimic homotopy theory.
There is one question on chat box.
Yeah. But is A X you can speak, right? Who is this?
Is the product of A and I the cylinder of A here in the example you get?
Is the
is A cross I equal to the cylinder of A here?
A cross I. Okay, wait a minute. No, of course not. The point is there is no cylinder, there is no interval object I. There is no I, right? That is the point. There is no I. Ideally, in the category of topological spaces, if you think of the terminal object, the singleton topological space, then the cylinder on the terminal object is actually the interval object, right? And if you try to mimic that for other areas to extract out an interval, given a cylinder, if you try to extract out an interval, this should rather be given by the cylinder on the terminal object, right? That you can expect maybe. And that's what I have done here. And I have shown you that that doesn't work. You cannot define a box right away. Okay. So, yeah, so throughout this whole discussion, I have given you several examples and I have given you messages that in the category of topological spaces, in the category of chain complexes, in the category of categories, the notion of equivalences are actually cylindrical equivalences for some particular cylinder. But there is some problem with this little notion of cylinder objects, which is as simple as doing nothing, which is just a factorization of this co-diagonal map, right? And it does not really tell you that the notion of homotopy that you define using this, where is that? Yeah, is an equivalence relation. Of course, this is reflexive. You can prove that along any cylinder object, F is homotopy to F itself, but not necessarily symmetric or transitive. Okay, in the case of chain complexes, this is symmetric and transitive, so good. In the category of, okay, what about in the category of categories? Then you fail actually. You see, if you take this particular interval I, forget about J now. If you take this particular example, then there is a problem. You see, if you say that this is an equivalence relation, then it better be symmetric, but it is not. If it is symmetric, then it would mean that if there is a natural transformation from F to G, eta, if there is a natural transformation, eta, from F to G, then there is a natural transformation from G to F, which is not the case, right? Which need not be the case. However, if we modify this to J, we will get a symmetric relation. But nonetheless, it is not necessary that for every cylinder object, the notion of cylindrical homotopy is an equivalence relation. If it is, then we are at a good position. But otherwise, this need not be the case. So in future lectures, we'll try to modify this and improve the cylinder structure in an arbitrary category. And the points that we are going to look at is when can we contract, when can we say, when can we say that cylinder on X is contracted to X. So this projection map is actually a contraction to X, is a contraction. See, in the category of topological spaces, you could actually contract the cylinder X. This projection map is actually a contraction. You are like contracting the whole cylinder to the topological space X. This is not just a projection. So you'll have to make sure that this P becomes a homotopy equivalence in the cylindrical definition. But this would become cyclic, right? If we first say that, okay, fine, there is a cylinder, and then using the same cylinder, we say that, okay, fine, this P has to be now a homotopy equivalent. That sounds ridiculous. You have to do something to it. Then the other thing is, there are subdivisions of the interval, right? Okay, first of all, I should define what is an interval object. Interval object in a category. I'll do that. It might or might not exist, of course. But once you have given me an interval, I can actually discuss some cylindrical structures. Then we should discuss when can we have subdivisions of cylinders. Subdivisions. By which I mean that in the case of topological spaces, we could actually, so if this is the cylinder on X, then you could actually break it down to half to concatenate homotopies, right? But a general cylinder structure on a category does not really allow you to break this cylinder down at the middle and concatenate homotopies. So we'll have to allow our cylinder object to have these subdivisions. Moreover, we have to identify the left and right endpoint. They should be interchangeable, meaning that we should have an involution.
Dipankar, time is already over. So
yeah, we are over. We are done actually. Involution on cylinders. And this will make sure that left and right endpoints are interchangeable, and the homotopy you define would become symmetric. Okay, so you'd stop here if there is a question. The take-home message is that many of the theories we study are actually somehow homotopy theory. Okay, we'll make it precise what homotopy theories mean, but not right now. So this is the end of the talk.
So any questions? There is a question on chat box.
Can we do all this by defining a right notion of mapping cone? Well, once you give me a cylinder, we can define a mapping cone. Who is this? Can you speak up? What do you mean by all this? Can you speak up actually? Dhruv? Dhruv, can you speak up? Okay, anyway, so I don't understand what you mean by all this, but nonetheless, once you have given me a cylinder object, you can talk about mapping cones and all. You can define mapping cones once you have a cylinder. Definitely. We'll come to that. We'll actually define all possible things. We will define path objects. Then we will define homotopy groups or loop spaces, omega, loop space functor. We'll also talk about suspension functor for arbitrary categories. Okay, this is for any arbitrary category. We'll define all homotopical tools possible once you have either a cylinder object or a path object. Yeah, all right. Any other question?
I think regarding that cylinder of 0.
Yeah.
Since you're not taking product with the terminal object is actually an isomorphism. So therefore, if an interval object exists, it has to be the cylinder of the terminal object, right?
Can you repeat?
Taking product with the terminal object is just an isomorphism. I mean,
taking a product with
the terminal object.
Yes.
So therefore, if the interval exists, I guess it has to be the, cylinder functor applied to the terminal object.
That's what I have done, right? That's what I have said. If there is at all an interval, it should be the cylinder on the terminal object. What is your question? What is your question?
No, I was just commenting that.
Oh, I see.
Okay, so if no other questions, then we can wrap up here. So we will meet on next Wednesday at same time. See you there. Okay, bye.